Welcome! In this session, we'll tackle an exciting problem from LeetCode, problem number 1339, maximum product of split binary tree. We'll explore the challenge, discuss potential approaches, and break it down step by step. Let's dive in. In this problem, you are given the root of a binary tree, and your task is to split the tree into two subtrees by removing exactly one edge. The goal is to maximize the product of the sums of the nodes in these two resulting subtrees. Since the result can become very large, you'll need to return the maximum product modulo 10 to the power of 9 plus 7. The input consists of the root of the binary tree, where each node contains an integer value, and the output is a single integer representing the maximum product of the sums of the two subtrees after the split. To better understand, let's look at an example. Consider a binary tree represented by the input array 1, 2, 3, 4, 5, 6. When visualized, the tree looks like this. The root node is 1, with two children 2 and 3. Node 2 has children 4 and 5, while node 3 has a single child, 6. If we cut the edge between node 1 and node 2, we create two subtrees. The first subtree contains nodes 2, 4, 5, which have a sum of 11, and the second subtree contains nodes 1, 3, 6, which have a sum of 10. The product of these sums is 11 multiplied by 10, giving us 110. This value is the output for this example. Now, let's consider another example where the binary tree is given as 1, null, 2, 3, 4, null, null, 5, 6. When visualized, the tree's structure is more skewed. Node 1 has only a right child, which is node 2. Node 2 has two children, 3 on the left and 4 on the right. Node 3 itself has two children, 5 and 6. If we cut the edge between node 2 and node 3, we again create two subtrees. The first subtree, consisting of nodes 3, 5, 6, has a sum of 14. The second subtree, made up of nodes 1, 2, 4, has a sum of 7. Multiplying these two sums gives us 14 times 7, which equals 98. The output for this example is 98. Let's look at a simpler case. Suppose the binary tree is represented by 1, 1. This tree is very small, with just two nodes. The root node is 1, and it has one left child, which is also 1. If we cut the edge between the root and its child, the tree splits into two subtrees. Each subtree contains just one node, and the sum of the nodes in each subtree is 1. The product of these sums is 1 multiplied by 1, which equals 1. For this example, the output is 1. Now, let's discuss some constraints and edge cases. The tree can have between 2 and 50,000 nodes, and each node's value is between 1 and 10,000. The tree is guaranteed to be valid, meaning it has no cycles or disconnected components. Edge cases include a minimal tree, with only two nodes, where splitting the only edge results in the simplest product calculation. Other edge cases involve highly skewed trees, which test the algorithm's ability to handle unbalanced structures, and very large trees, which ensure the solution is efficient even when the input size reaches its upper limit. To solve this problem, we follow a systematic approach. First, compute the total sum of all nodes in the tree. Next, perform a depth-first search, or DFS, to calculate the sum of nodes for each subtree. For every subtree, calculate the product of the subtree's sum and the sum of the remaining portion of the tree, which is the total sum minus the subtree sum. Keep track of the maximum product encountered during these calculations. Finally, return the maximum product modulo 10 to the power of 9 plus 7. This approach ensures that the solution is both accurate and efficient, even for large trees, as each node is visited only a limited number of times. To tackle the problem of finding the maximum product of the sums of two subtrees when splitting a binary tree, we need to carefully consider our approach. One straightforward method is the brute force approach. Here, the idea is to compute the sum of nodes for every possible way the tree can be split. For each split, we calculate the product of the two resulting subtree sums and track the maximum product obtained. However, this method involves significant redundancy, as calculating the sum for each edge removal requires traversing the entire tree repeatedly. This leads to an O(n)² time complexity, which is inefficient for large trees. To improve on this, an optimized two-pass DFS approach can be used. The key insight here is that we can avoid redundant calculations by splitting the process into two steps. First, we calculate the total sum of the tree in one depth-first traversal. Then, in a second traversal, we compute the subtree sums and evaluate the product for each possible split. Importantly, the complement of a subtree can be derived as the total sum of the tree minus the sum of the current subtree, eliminating the need for redundant computations. This insight allows us to significantly optimize performance. The two-pass DFS approach proceeds systematically. In the first step, we perform a depth-first search to calculate the total sum of the tree. Once this total is known, we use a second DFS to calculate the sum of each subtree and compute the product of the subtree sum with its complement, which can be derived as total_sum, subtree_sum. During this process, we continually update the maximum product encountered. This approach has a time complexity of O(n), as each node in the tree is visited exactly twice, once during each DFS pass. The space complexity is O(h), where h represents the height of the tree, due to the recursion stack. This makes the approach highly efficient for large trees. Additionally, by separating the computation into two distinct passes, the logic remains modular and easier to understand. An alternative to this is a single-pass DFS, where the total sum of the tree and the evaluation of products are performed simultaneously within a single traversal. While this reduces the number of traversals, it introduces more complexity into the implementation. Debugging and maintaining such a solution can become challenging, especially for larger or more intricate trees, which is why it may not always be the preferred choice. The optimized two-pass DFS approach was ultimately chosen for this problem because it strikes the right balance between efficiency and simplicity. By clearly separating the two concerns, first calculating the total sum and then evaluating potential products, this method avoids redundant calculations while maintaining a modular structure that is easier to debug and reason about. A key insight that made this approach so effective was recognizing that the complement of a subtree could be derived as total_sum, subtree_sum. This eliminated the need for additional computations to determine the sums of both subtrees for every split, saving significant time. When comparing this to the single-pass DFS, while the latter might seem faster in theory by combining the two traversals, the added complexity in logic does not justify the minor gains in performance. The two-pass DFS simplifies the implementation while delivering optimal efficiency, making it the most practical choice for solving this problem effectively. To solve the problem of maximizing the product of the sums of two subtrees after splitting a binary tree, we need an approach that is both efficient and methodical. The first step in our algorithm is to calculate the total sum of the tree. This is done using a recursive function that traverses every node in the tree. For each node, we compute its subtree sum by adding the node's value to the sums of its left and right subtrees, which are also calculated recursively. Along the way, we store the total sum of the tree, as this value is critical for later steps. By pre-computing the total sum in a single traversal, we ensure that our algorithm is efficient, with a time complexity of O(n), where n is the number of nodes in the tree. This sets the foundation for evaluating all potential splits in subsequent steps. Now that we have the total sum of the tree, the next step is to evaluate all possible splits. We achieve this by traversing the tree again recursively. At each node, we use the pre-computed subtree sums to determine the sum of the subtree rooted at the current node. From this, we can calculate the sum of the other subtree that would result from splitting the tree at this node. Specifically, the other subtree's sum is the total sum of the tree minus the current subtree sum. The product of these two sums is then computed, and we keep track of the maximum product encountered during the traversal. By visiting each node exactly once, we efficiently evaluate all potential split points, keeping the overall complexity O(n). Finally, since the product can grow very large, we return the result modulo 10 to the power of 9 plus 7, ensuring that the value remains within standard integer limits and avoids overflow. The efficiency of this approach lies in its design and the data structures used. The input is a binary tree where each node has a value and pointers to its left and right children. During the recursive traversal, we use variables to store intermediate results such as the subtree sums and the total sum. These variables eliminate redundant calculations, as the subtree sums are computed only once. Additionally, the algorithm is robust against various edge cases. For instance, if the tree has only a single node, the product is 0 since no split is possible. The algorithm also handles trees with negative node values seamlessly, as the sum calculations naturally incorporate these values. Moreover, the O(n) complexity ensures that the solution scales efficiently, even for large trees with up to 10 to the power of 4 nodes, meeting the problem's constraints. Let's walk through an example to see the algorithm in action. Consider a binary tree with the structure: the root node has a value of 1, with left and right children 2 and 3, and the left child 2 has 2 children, 4 and 5. First, we calculate the total sum of the tree. The subtree sums are as follows: for node 4, it's 4, for node 5, it's 5, for node 2, it's 11, for node 3, it's 3, and for the root node, it's 15. The total sum of the tree is 15. Next, we evaluate possible splits. Splitting at node 4 gives a product of 4 times 11, which is 44. Splitting at node 5 gives a product of 5 times 10, which is 50. Splitting at node 2 gives a product of 11 times 4, which is 44. Finally, splitting at node 3 gives a product of 3 times 12, which is 36. The maximum product is 50. We return this value modulo 10 to the power of 9 plus 7, which is still 50. This demonstrates how the algorithm efficiently identifies the optimal split point. Here, we start by importing the ru_cache decorator from the functools module, though it's not explicitly used in this implementation. The goal of our function is to find the maximum product of the sums of two subtrees after splitting a binary tree. Inside the solution class, we define the maxProduct method, which takes the root of the binary tree as input. To handle large numbers, we use a modulo value, 10 to the power of 9 plus 7, which ensures our result remains within bounds. The first step is to calculate the total sum of all node values in the tree. This is done using the calculate_total_sum helper function, which recursively adds the value of the current node to the sums of its left and right subtrees. If the node is null, we simply return 0. Once we have the total sum of the tree, we initialize a class variable, self.max_product, to track the maximum product we encounter as we evaluate different ways to split the tree. Next, we define another helper function, find_subtree_sum, which is responsible for exploring all possible splits and calculating their corresponding products. The find_subtree_sum function is where the product calculation happens. For each node, it recursively calculates the sum of the current subtree, which includes the node's value and the sums of its left and right subtrees. Using this subtree sum, we compute the product of its complement, which is the total tree sum minus the current subtree sum. This represents the product of the sums of the two resulting subtrees if we were to split the tree at this point. We then compare this product with self.max_product, updating the latter if the current product is larger. Finally, the function returns the subtree sum, enabling the recursion to proceed. Once the recursive calls are complete and all possible splits are evaluated, we return the maximum product found, modulo 10 to the power of 9 plus 7, as the solution. Here, we begin by defining the structure of a binary tree node with the treeNode class. This class includes fields for the node's value, as well as references to its left and right child nodes. Multiple constructors are provided to handle different initialization scenarios, such as creating an empty node, a node with just a value, or a node with both a value and children. Moving on to the solution class, we define two key variables, mod, which represents the modulo value of 10 to the power of 9 plus 7 to handle large numbers, and maxProduct, which will keep track of the maximum product of a tree split. Additionally, we define totalSum to hold the sum of all the values in the tree, which will be computed later. These variables are essential for solving the problem efficiently. The main method, maxProduct, is where the solution logic begins. In the first step, we calculate the total sum of the tree by calling the helper method calculateTotalSum and passing the root node. This method will recursively traverse the tree and sum up all the node values. Once we have the total sum, the second step involves finding the maximum product by evaluating all possible ways to split the tree. This is done using the findSubtreeSum helper method, which we'll explore shortly. Finally, after determining the maximum product, we return the result modulo 10 to the power of 9 plus 7 to ensure the output adheres to the constraints. The calculateTotalSum method is straightforward. It performs a depth-first traversal of the tree, summing up the values of the current node, its left subtree, and its right subtree. If the node is null, it simply returns 0, ensuring the recursion terminates properly. The find subtree sum method is where we calculate the sum of each subtree and determine the product of the split. For a given node, we compute the subtree sum by summing the node's value, the left subtree sum, and the right subtree sum, all calculated recursively. With this subtree sum, we can evaluate the product of splitting the tree at this point. The product is determined by multiplying the sum of this subtree with the sum of the rest of the tree, which is the total sum minus the subtree sum. We then compare this product with the current max product and update max product if the new product is greater. Finally, we return the subtree sum so that it can be used in the calculations higher up in the recursion stack. This recursive approach ensures that we evaluate all possible splits efficiently. To solve this problem, we start with a simple binary tree consisting of 3 nodes. The root node is 1, with left and right children 2 and 3, respectively. The first step is to compute the total sum of all node values in the tree. At the root node, we calculate the sum of its left subtree, which is just the value of node 2, and the sum of its right subtree, which is the value of node 3. Adding these values together with the root node's value gives us a total sum of 6 for the entire tree. This total sum will be essential for determining the maximum product of a split. Now that we have the total sum, we move on to finding the maximum product of splits. Starting at the root node, splitting the tree here would leave the entire tree intact, so the product is 0 and an invalid split. At the left child, node 2, the subtree sum is 2. The complement, or the sum of the remaining part of the tree, is 6 minus 2, which equals 4. The product of these two parts is 2 times 4, resulting in 8. Similarly, at the right child, node 3, the subtree sum is 3, and the complement is also 3. The product is 3 times 3, giving 9. Among these splits, the maximum product is 9. Since the result is already less than 10 to the power of 9 plus 7, the final output is simply 9. Next, we analyze a larger binary tree with 5 nodes. The root node is 1, with left child 2 and right child 3. Node 2 further branches into 4 and 5 as its left and right children. To compute the total sum, we begin at the root. For the left subtree rooted at node 2, we calculate the sums of its children. Node 4 contributes 4, and node 5 contributes 5. Adding these values with node 2's value gives a subtree sum of 11. For the right subtree rooted at node 3, the sum is simply 3. Combining these with the root node's value gives a total sum of 15 for the entire tree. With this total sum, we are ready to calculate the maximum product of splits. Starting the split calculations, at the root node, a split here results in a product of 0, which is invalid. At the left child, node 2, the subtree sum is 11, and the complement is 15 minus 11, which equals 4. The product of these two parts is 11 times 4, yielding 44. At the right child, node 3, the subtree sum is 3, and the complement is 12. The product is 3 times 12, resulting in 36. Moving further down, at node 4, the subtree sum is 4, and the complement is 11. The product of these parts is 4 times 11, giving 44 again. Finally, at node 5, the subtree sum is 5, and the complement is 10. The product is 5 times 10, which equals 50. Among all these splits, the maximum product is 50. Since it is already less than 10 to the power of 9 plus 7, the final output is 50. Now, let's examine a skewed binary tree where all nodes are aligned to the right. The root node is 1, which has a right child 2, and node 2 further has a right child 3. To compute the total sum, we start at the root. For the right subtree rooted at node 2, we calculate the sum of its right child, node 3, which is 3. Adding this to node 2's value gives a subtree sum of 5. Including the root node's value, the total sum of the tree is 6. With this total sum, we proceed to find the maximum product of splits. For the split calculations, at the root node, the product is 0, making it an invalid split. At the right child, node 2, the subtree sum is 5, and the complement is 6 minus 5, which equals 1. The product of these two parts is 5 times 1, yielding 5. At the right child's right child, node 3, the subtree sum is 3, and the complement is also 3. The product is 3 times 3, which equals 9. Among these splits, the maximum product is 9. Since this value is already less than 10 to the power of 9 plus 7, the final output is simply 9. To analyze the time complexity of our solution, we need to consider the two main steps involved. First, calculating the total sum of all nodes in the binary tree using the calculate_total_sum function. This function traverses the tree recursively, visiting each node exactly once. For each node, it performs constant time operations, such as adding the node's value and making recursive calls. As a result, this step has a time complexity of O(n), where n is the total number of nodes in the tree. Next, we evaluate the maximum product of all possible splits using the find_subtree_sum function. This function also traverses the tree recursively, visiting each node exactly once. During this traversal, it calculates the subtree sum and computes the product of the split in constant time for each node. Therefore, this step also has a time complexity of O(n). Combining these two traversals, the total time complexity of the solution is O(n). Both calculate_total_sum and find_subtree_sum are recursive functions, so the space complexity is influenced by the recursive call stack. Now, let's consider the space complexity. In the worst-case scenario, where the binary tree is completely skewed, the recursion depth will be equal to the total number of nodes, which is n. Thus, the space complexity in this case is O(n). On the other hand, for a perfectly balanced binary tree, the maximum depth of recursion corresponds to the height of the tree, which is O log n. Hence, the call stack contributes O(h) space, where h is the height of the tree. Additionally, since no extra data structures are used for intermediate calculations, the auxiliary space usage is O(1). Therefore, the total space complexity is dominated by the recursive call stack, O log n in the best case and O(n) in the worst case. Let's compare this optimized approach to a brute force solution. A naive method would involve splitting the tree at every possible edge and calculating the product for each split. For each split, the sums of the resulting subtrees would need to be computed, which would require traversing the entire tree. Since a binary tree with n nodes has n1 edges, this brute force approach would require a traversal for every edge, resulting in a time complexity of O(n squared). In contrast, the optimized solution avoids redundant computations by calculating the total sum in the first traversal and reusing it in the second traversal. This eliminates the need to recompute subtree sums for each split, reducing the time complexity to O(n). As a result, the optimized approach is significantly more efficient than the brute force method. To summarize, the optimized solution has a time complexity of O(n), as it involves two linear traversals of the binary tree. The space complexity is O(h), where h is the height of the tree. In the best case, for a balanced tree, the space complexity is O log n, while in the worst case, for a skewed tree, it is O(n). In comparison, the brute force approach has a time complexity of O(n squared, making the optimized approach far more efficient in practice. This balance of time and space efficiency makes the solution well suited for handling large binary trees. One of the most common mistakes in this problem is failing to calculate subtree sums correctly. Remember, the sum of a subtree isn't just the value of the root node but also includes the sums of all its descendant nodes. Forgetting this can lead to incorrect results. Another issue arises when the tree contains duplicate subtree sums. If your code doesn't account for this, it might select the wrong split and produce a suboptimal product. Additionally, edge cases like very small trees can be tricky. For example, trees with only one or two nodes might not allow valid splits under the constraints, so your solution needs to handle these carefully. Inefficiency is another common pitfall. Some solutions recalculate subtree sums repeatedly, which wastes time. Instead, you can use a post-order traversal to compute these sums efficiently in linear time. Lastly, when working with large trees, product calculations might exceed the limits of your data type. To avoid overflow, it's important to use modular arithmetic, such as taking results modulo 10 to the power of 9 plus 7. Now, from an interview perspective, proficiency with tree traversals, particularly post-order traversal, is crucial for this problem. Post-order traversal allows you to compute subtree sums efficiently, which is the foundation of the optimized approach. Another key interview point is optimization. Reducing redundant computations is vital. By pre-computing values like the total tree sum and individual subtree sums, you can save significant time. You should also be ready to explain how your solution handles edge cases, such as unbalanced trees, single-node trees, or trees with repeated values, as these are common discussion points. Furthermore, interviewers may ask you to compare a brute force approach, which evaluates all possible splits, with the optimized approach that uses post-order traversal. Understanding the trade-offs between these methods demonstrates a deeper grasp of the problem. Lastly, exploring related problems can help strengthen your understanding. Problems like finding the diameter of a binary tree or the maximum path sum often involve similar traversal techniques and concepts, making them excellent practice. When it comes to alternative approaches, a brute force method involves computing the sum of all possible subtrees and evaluating their splits. While this approach is simple to understand, it's computationally expensive, with a time complexity of n squared. A more efficient solution uses optimized post-order traversal. This approach performs a single traversal to calculate all subtree sums while simultaneously keeping track of the maximum product, reducing the time complexity to n. Another less common but intuitive approach is the top-down method. Here, you start with the total tree sum and recursively evaluate potential splits, updating the maximum product during each step. This method also achieves n time complexity and offers a different perspective on solving the problem. Both optimized approaches are highly effective, but understanding their nuances can help you choose the best fit depending on the context. Great job! Today, we learned how to efficiently solve the maximum product of split binary tree problem by combining binary tree traversal with optimization techniques. Remember, practicing these types of problems sharpens your problem-solving skills. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!